Okay, welcome to Let's Get to the Marks. I'm going through the Physics and Maths Tutor pack for Aromatic Chemistry for A Level Chemistry AQA. It's a revision pack you can find on the awesome Physics and Maths Tutor website. Let's get into it. Paracetamol is a medicine commonly used to relieve mild pain. Traditionally, paracetamol has been made industrially in a three-step synthesis from phenol. So here we have a reaction synthesis where we can see phenol was step one, and then it's changing with each step of this three-step reaction. We can see nitrate group added, then an amine group, and finally we've got like a carbonyl group added. So name the mechanism for the reaction in step one between phenol and 4-nitrophenol. So in order to understand this, let's look at what's taken place between phenol becoming 4-nitrophenol. So what have we added? We've added NO2, and you need to know this off by heart. It's one of your key bits of content. What happens is the nitronium ion, which is a cation, it's got a positive charge. This is an electrophile because of its positive charge. It seeks out electron-rich areas, and the electron-rich area in a benzene ring is the delocalized ring. So a pair of electrons break out of the delocalized ring and go towards this cation here. And then what we have is a horseshoe forming. Remember, these points on the benzene have hydrogen attached, so the NO2 group attaches where one of the hydrogens attaches. In order to restabilize the ring, the bond with the hydrogen breaks, and the pair of electrons from that hydrogen bond go back into the ring, reform the delocalized ring. So this is basically a substitution reaction, and we start with an electrophile because the NO2 plus is positive and seeks out electron-rich areas. So we're looking at electrophilic substitution. Okay, as I work through this Physics and Maths Tutor pack, this is only part one of three. This is the first video of three. I suggest at the start of each part to a question, i.e. question 1, A, B, C, D, E, F, G, at the start of each one, you pause the video, read through the question, and then have a go yourself on a scrap bit of paper, which you can throw away afterwards. Then you unpause and watch the walkthrough. Now, I'm only covering one question in this aromatics pack, but I'll be covering the rest of it in two more videos. Okay, so in this part B, we need to complete the equation for the reaction in step 2. And you've got 4-nitrophenol here at the start. So the nitro group's not as high priority as the hydroxy, so it's called 4-nitrophenol. And then it forms 4-aminophenol. Again, the amino group's not as high priority as the hydroxy. So essentially, we just need to complete this equation now. And you've got to think about these two oxygens here on the nitrogen have been swapped for these two hydrogen here on the amine group. So we're taking the two oxygens off the nitro group and replacing them with two hydrogens. So we're going to need to add hydrogen in this reaction. We need to plus H2. But the question is, how many hydrogens do we need to add? And what is going to be formed when we remove the oxygen atoms from the nitro group? Of course, when you remove oxygen atoms from something and you've got hydrogen as a reactant, you're going to form what molecule? And how many oxygens are removed? This is going to tell you how many molecules of our product will be formed. Of course, when you add oxygen and hydrogen together, you're going to make water as a side product. So our side product is going to be a 4-aminophenol, but we're going to have H2O as the side product. Now the question is, how many H2Os? Well, we're removing two oxygens, and each H2O has one oxygen, so we're going to need two H2O. However, don't forget, we're also adding on another two hydrogens to form the amine group. So altogether, we're going to need three hydrogen molecules to make this work. Big shout out to Noor Shah for pointing out my mistake in my earlier rendition of this video. Although I had circled the H2 on the amine group, I completely forgot to add it on when going through my walkthrough. Okay, now this reaction, this is just a side note, you don't need it for this question. You can use hydrogen with platinum, palladium, or nickel catalyst. It's called hydrogenation when you're adding hydrogen to something. But you can also use, in AQA, they love to say tin with hydrochloric acid. Yeah, I say a lot, so yeah, and another one. All right, guys, moving on. Let's go. So let's look at part C. In theory, either ethanoyl chloride or ethanoic anhydride could be used in step 3. Complete the mechanism for the reaction of 4-aminophenol with ethanoyl chloride. RNH2 is used to represent 4-aminophenol in this mechanism. So the R group here is actually the product of step 2. I've done the old again. So what we want to do is we want to draw a hydroxy group because it's 4-amino phenol hydroxy being more important. And then, so you always name the hydroxy after the amine group there. So then we got the amine group at the bottom. Now that is going to be represented in this by this R over here. So we're just writing R with the NH2. So the R really represents the benzene with the hydroxy on it. You can see here the lone pair from the nitrogen is attacking that carbon because that's delta positive due to the polarized bond of the C-O-O bond. The oxygen, they're showing a curly arrow going from the double bond to the O. You should know what that represents. That means we're going to end up with a lone pair because each arrow is worth 2 electrons. So we're going to end up with a lone pair on the oxygen and a negative charge. We've got the methyl group and then we've got the chlorine atom coming off. And of course, we've now attached nitrogen and 2 hydrogen atoms. And we've got the R group. Now, here's our first problem. Nitrogen isn't supposed to have 4 bonds. It normally has 3 bonds coming off it. What happens to a nitrogen when you have 4 bonds around it? Think of the ammonium ion. What charge does nitrogen get? You should realize that the nitrogen atom will now have a positive charge on it because it has 4 bonds. So we always count the bonds around a nitrogen atom when we're doing mechanisms. And if there's 4 bonds around the nitrogen, we want to put a positive charge. Okay, so it's like a nitronium ion or whatever it is. But it has a positive charge. Now we look up here, the oxygen is going to donate its pair of electrons back. So whenever you see the oxygen like this, when temporarily that carbonyl bond has been broken, it's going to reform. And that would mean that carbon would have 5 bonds around it and carbon can't have 5. So the chlorine's got to be sent off. So our chlorine's going to break off. The carbonyl bond that was temporarily destabilized will reform. And then over here, one of these hydrogens, I'm not going to do this one because it looks a bit confusing. I'll do this one down here. One of these hydrogens its bond is going to break and the pair of electrons from the bond are going to go to that positive nitrogen and stabilize the molecule by donating their electrons to the nitrogen. And that's going to leave us with a hydrogen ion coming off the side here. And of course, you've got a chlorine ion coming off the side here. Now, again, the product is not part of the marks. That's not what they want here. They want the mechanism. So they're looking for curly arrows and lone pairs and charges. So those 3 curly arrows, the plus and the lone pair with the minus on the oxygen, that's going to get you your 3 marks or your 2 marks in this case. A lot of work for 2 marks. This is the product, what you'd end up with, which I've drawn here. But you'd also get a chloride ion released where the chlorine bond is broken, and where one of the hydrogens breaks to stabilize that positive nitrogen, you're going to get a hydrogen ion, and you guys can guess what the product is going to be, the side product. It's going to be HCl. Now, this is not part of this question. The part of the question is that first bit I've drawn there with the 3 curly arrows, the plus, the minus, and the lone pair, and that will get you the 2 marks. Okay. It is important to know that you form hydrogen chloride as a side product and to be able to work out what your side products are, as we'll see in the next part of the question. Let's move on. Keep moving on, keep moving on, keep moving on, keep moving on. In practice, ethanoic anhydride is used in the industrial synthesis rather than ethanoyl chloride. Give one reason why ethanol chloride is not used in the industrial synthesis. Pause the video, see if you can have a go, and then unpause and watch the walkthrough to the answer. Okay, let's do it. So, looking green here with the ethanoic anhydride, the green bit of the ethanoic anhydride, what do you think that's going to go on to form when it combines with a hydrogen ion? Now look at the ethanoyl chloride and the bit that I've highlighted in green. That's the bit that's going to break off in the mechanism and join with the hydrogen ion that also breaks off. So what's the difference in the side products that they're going to form. And that's going to give you the answer to the question. So let's take a look back at the original reaction mechanism for the question before, and then we're going to be able to work this out. So this is the reaction mechanism from the question before. If I zing this down into place, I put this up for the last question, how we worked out the mechanism. But look what happens. The chlorine atom breaks off. When you've got ethanoyl chloride, the CH3, C double bond O, and the chlorine atom, look, the chlorine atom is going to snap off. Remember that one of our H's comes off in the middle part of that mechanism as well to neutralize that positive carbon atom. And so that's going to form hydrogen chloride. However, if it was acid anhydride, um, what would happen instead is, instead of a chlorine coming off, the bit I highlighted in green earlier was a carboxylate group. And that carboxylate ion that comes off instead will combine with the hydrogen from the nitrogen to make like ethanoic acid, which is vinegar, essentially. And so what's the difference in danger between hydrogen chloride and vinegar? What's the difference, and why might people prefer to use the acid anhydride and get the ethanoic acid side product than hydrogen chloride? And that will get you your answer if you can work that out. So of course the CH3COO with a minus charge, or carboxylate ion, breaks off, joins with the hydrogen ion, and you get CH3COOH, and of course that's the formula for ethanoic acid. So the acid anhydride tends to be a safer reaction than using ethanoyl chloride. So in practice, give a reason that we use ethanol chloride in industrial synthesis, and it's because it forms ethanoic acid instead of hydrochloric acid. Or HCl fumes hydrogen chloride, which is a gas, sorry, not an acid. But hydrogen chloride fumes, HCl, are corrosive, whereas ethanoic acid is not corrosive. Okay, cool. That was a bit of a long waffle for a 1-mark question, but I hope it helps. And if you're liking the video, make sure you hit the like, subscribe to the channel, and share. Leave a comment. Encourages me to make more of these videos to help you get through your A-level chemistry. Okay, let's get to the next question. In step 3, other aromatic products are formed as well as paracetamol. Draw the structure of one of these other aromatic products. So we're going to need to go back and look at what's happening in step 3, because there's some other products that aren't shown in this mechanism that are formed. So let's go back and have a look. So if we zing back up here and we look at step 3, what it's shown us is that we've ended up with our CH3CO taking the place of one of the hydrogens on the amine part of this compound. Instead, we can have the oxygen on the hydroxy group attack that delta positive carbon. And we're not going to go through the whole mechanism, but a simplified version of it is that the oxygen lone pair that's on the hydroxy group attacks that carbon atom on the polar carbonyl bond, and we get the carbonyl bond attaching there, essentially. So this is a bit oversimplified because you'd have the chlorine attached, etc. There'd be the chlorine would be breaking off and the hydrogen would be breaking off to form a hydrogen chloride side product, the same. But essentially I'm just trying to show you here that it could attach there to that oxygen, and we could kind of get like an ester link formed at the top here with an O to a C double O with a methyl attached. So that's our other option there that can be formed as a side product instead. And I'll draw the structure of that out here so you can see that. And there you go. Only 2 more parts to do for this question. That structure there that I've circled is the answer. It's just kind of showing you a bit of working beforehand, even though it wasn't fully correct. Let's move on to the next bit. So we're looking at F here. Chemists have recently developed a 2-step process to produce paracetamol from phenol. In the first step, phenol is oxidized to hydroquinone. As we can see there, we've got a phenol group, we've got hydrogen peroxide attacking it, and then we've got like well, I can't even say that. What is it? Hydroquinone, where you've got a hydroxy group 2 opposite each other across the benzene, and water formed. In the second step, hydroquinone reacts with ammonium ethanoate to form paracetamol, complete the equation. So do you know the formula for ammonium ethanoate? Think about it. Ethanoate, it's a carboxylate ion. It's CH3COO with a minus. It's a carboxylic acid where the hydrogen's been removed, and it's been replaced with another positive ion instead of a hydrogen ion. And this time it's the ammonium ion. You should know the formula from GCSE. It's NH4+. So that's our formula for ammonium ethanoate. So let's have a look here at what's different in the reactants to the products. And what you should find is that if you look at the carboxylate group, the CH3COO, we've only got one O. There's only one O now, so it's lost an oxygen. Also, look where the hydroxy group was. That's lost an oxygen too. And we've lost 4 hydrogens, 3 from the NH, and it could be the H from the hydroxy's gone as well. But a total of 4 hydrogens and 2 oxygens have come off, and that means we need 2 water molecules to balance it all up. Okay, we're coming to the last part of the walkthrough here. So don't forget to smash the like, subscribe, and let's get into the final bit of the walkthrough. So let's calculate the mass in kilograms of hydroquinone MR110 needed to produce 250 kilograms of paracetamol. So what we need to do here is we've got a mass and we've been given MR. This should strike clues in your brain. What's the equation? It's going to be mass over MR times moles. Let's just draw out the structure of the hydroquinone. So we know that it's got 2 hydroxy groups and it has an MR of 110. We don't know the mass of hydroxyquinone, just checking out the formula for the paracetamol now. So now I can draw out the paracetamol. Just had to have a sneaky look back there because I can't remember this off by heart. Got a hydroxy group down up there, up the top, and then down the bottom, another quick double check, NH. Okay, NH, we had CH3 coming off and then a carbonyl bond. Awesome. We need our mass over MR times moles. Let's get into it. It's a 1-to-1 reaction. It shows us that in the step. So we need that for coefficients. When you're finding out the mass of something and you've got the mole and you can work out the moles of something else, then you know that once you worked out the moles of one, you worked out the moles of the other. So my first thing is I've been given I need to find out. I've been given 250 kg of paracetamol. So from the formula, I can work out its MR. I think it's got 8 carbons there. Notice I've drawn the hydrogens on to make it easy for me to add up. It's got 9 hydrogens, 1 nitrogen atom, and 2 oxygens. So if I add that all up, 8 times 12 is 96. I've got 9 ones for the hydrogen, 14 for the nitrogen, 32 for the oxygen. Smash that all in the calculator. And that equals 151, and that's our MR of paracetamol. We know we got 250 grams, times that by 1,000 because we use grams in amount of substance in chemistry. We don't use kilograms. So we want 250,000 grams, which is our mass, divided by the MR of 151, and we get 1,655.6 moles. Now, I'm going to times that by 110, but let's just explain why. So that's my moles of paracetamol. Remember I said it's a 1-to-1 ratio. If I know that I have 1,655.6 moles of paracetamol, as it's a 1-to-1 ratio, I know I've got the same moles of hydroquinone. Now, luckily they've given us the MR of hydroquinone. They don't want us to do that same thing twice where we have to calculate the MR. So we're just going to do 110 times the 1,600 and 55, God, I lost my train of thought there, 0.6 moles. So we're going to multiply those together. And what we're going to get when we do that is 182,116 grams. But don't forget, we need to convert that to kilograms. So take that answer from your calculator and divide by 1,000, and you'll convert that into kilograms. And that's going to end up being 182.116 kg. Now we can round in A-level chemistry to 3 sig figures, so we can just call it 182 kilograms. Propanol, chloride, and benzene is an example of acylation, which is the correct representation of the part of the mechanism of this reaction. Okay, so look at A. First of all, what we have with A, we're looking at the reaction of propanol, chloride, and benzene, and just any part of that mechanism. So what's wrong here? Well, the chlorine normally breaks off during acylation to leave the cation. And here it's showing the chlorine donating a pair of electrons to that single bond. That would become a double bond. That's not possible with chlorine. That's not how it reacts. The arrow should be going the other way from the bond back to the chlorine. So that one's wrong. Now let's check out B. B shows AlCl3 donating a pair of electrons to chlorine. Again, aluminium is not an electron donor. It's only got 3 electrons in the outer shell, if you think back to basic GCSE modelling. So it doesn't have a spare pair of electrons to donate to the chlorine. What normally happens when it forms AlCl4 is the chlorine donates a pair of electrons to the aluminium, which it can accept in its outer shell because it has room. So that's completely wrong too. If we go down to D here, not giving you any hints at the answer, of course, but if we go down to D here, we can see the bond. From the acyl group being donated next to the carbonyl bond, being donated to stabilize the benzene ring. Actually, what happens during substitution onto the benzene ring is that one of the hydrogen atoms attached to a carbon atom on the benzene ring donates its pair of electrons from its bond back to destabilize the broken ring or the horseshoe shell. And there we go. Those 3 answers are all incorrect. And of course, the correct one is C. And what we can see with C, a curly arrow, which represents a pair of electrons being donated to that positive carbon atom on that cation there. And that would make sense. Carbon's only got 3 bonds there. It's willing and able to form another bond. It's ready to accept a pair of electrons, and it gets that from the delocalized ring, which is temporarily broken and then reformed when the hydrogen donates the electrons back. Okay, let's zing on to the next question. So that one's correct. Now we want to bust down and look at question 3. Okay. So for question 3, data about the hydrogenation, fancy word, means adding hydrogen, of cyclohexene and of benzene are given. We can see for cyclohexene, which has 1 double bond, the enthalpy of hydrogenation is minus 120 kilojoules per mole. The minus means it's exothermic. And for benzene, adding 3 hydrogen molecules is minus 208 kilojoules per mole. Now, you might expect it to be minus 360, 3 times more than cyclohexene. Explain the bonding in the shape of the benzene molecule. Compare the stability of benzene with that of the hypothetical cyclohexa 1,3,5 triene molecule. Use the data in your answer. This is a 6-mark question. It's basically broken it down for you, saying you're going to get 2 marks for each section. It's basically mentioned that you need to talk about the bonding in benzene, you need to talk about the shape of benzene, and then you need to talk about the stability of benzene. So that's actually in that stem of the question of A. So why don't you pause the video, have a go, see if you can talk about the bonding for 2 marks, the shape, and the stability. Unpause the video, and then we'll go through the answers. Okay, bonding. Each carbon atom is covalently bonded to 3 other atoms. So think about a benzene ring. It's got a carbon atom either side of it and 1 hydrogen coming off. Obviously, C6H5 is the formula for benzene. So what's unusual about that is that normally carbon, which is in group 4, would have 4 electrons in its outer shell. So it would have 2s2 and 2p2. However, one of those electrons has been stuck into, one of those unpaired electrons has been dumped into the middle of the benzene ring to form the delocalized ring of electrons. And this is where the p orbitals, so the electrons from those 2 p orbitals in each of the 6 carbon atoms, 1 electron from the 2 p orbitals has been shoved in there and has overlapped to form what's called a pi cloud. And so, yeah, that's all you need to discuss on the bonding in order to get the 2 marks. Now, for the next 2 marks out of the 6, what you're going to need to do is talk about the shape, because that's what it basically alluded to in the question, or the stem of the question. So the shape of a benzene molecule is planar, which means the hexagonal ring is all in one plane. So think of a piece of paper just held sideways while you're looking at it. And the carbon atoms, the 2 carbon atoms to the hydrogen in each corner, or the carbons all in the ring, they all have a trigonal planar shape and a bond angle of 120 degrees. The delocalized ring, which is inside that hexagonal ring is actually spread above and below the ring, a little bit like the buns on a burger. If you imagine the hexagonal ring is the meat in a burger, and then the bun at the bottom and top is the delocalized cloud poking up and down below. And that's formed because of all the overlapping p orbitals. Now, the next mark that we would get, the next 2 marks, is for talking about the stability of a benzene compared to the cyclohexatriene, whatever the numbers were. I can't be bothered to go back up and look, but the cyclohexatriene, it had 3 positions. I don't know, 2, 4, 5, whatever, 2, 3, 5, whatever it was, or 1, 3, 5, whatever it was. So the stability of the cyclohexatriene is shown to be less stable than the benzene ring. And why is that? Well, the enthalpy of hydrogenation of cyclohexatriene is 360 because it's 120 kilojoules per mole exothermic hydrogenation of each double bond, and cyclohexatriene has alternating double and single bonds. However, benzene, you would think, might be similar, but it only has 200 or minus 208 kilojoule per mole. So it's less exothermic, its enthalpy of hydrogenation. And this is because of the increased stability of the benzene ring. We actually say that the minus 152 kilojoules less exothermic that it is known as the energy of stabilization. The bond lengths of the benzene within the carbon atoms all around the benzene are in between the bond length of a single and double bond, whereas in the hexatriene they actually have double bonds, then single bonds, and of course double bonds are shorter, single bonds are longer, and this decreases the stability of the hexatriene, the fact that the bond lengths are all different, whereas in a benzene ring the bond lengths are all the same. It's in between the bond length of a double and a single carbon-carbon bond. Moving on to the final bit, the enthalpy of hydrogenation of cyclohexa 1,3-diene is not exactly double that of cyclohexene, so just the value for the enthalpy of hydrogenation of cyclohexa 1,3-diene and justify your value. So we might think that when you've got one double bond in a cycloalkene, that to add hydrogen across it costs you or releases minus 120 kilojoules per mole. If you had 2 double bonds, right, it should be minus 240 kilojoules per mole. But so what they're saying is it isn't minus 240. And you'll get a mark for saying actually it's less than 240. And you need to state somewhere between minus 121 and minus 249 so that you've appreciated that it's more than minus 120. More exothermic than minus 120, but less exothermic than minus 240. So it's a bit more stable because it releases less energy when hydrogenated, which means it's at a more stable position. Now, why is it more stable? The reason why the diene is more stable is to do with the distance between the 2 double bonds. The 2 double bonds are actually only one single bond apart, and this means there's some overlap between the p orbitals in the double bond and some delocalization which stabilizes it. Now, if you look at my incredible drawing in black here, you can see in this diene, the 2 double bonds are more than one single bond apart. This means there's less overlap between the p orbitals, less delocalization, and we would expect that to have an enthalpy of hydrogenation closer to minus 240, if not minus 240, because there's barely any delocalization and the extra stability that that provides. But whenever the single bonds in a diene or a triene are, well, which they would in a triene, but whenever they're in a diene, they're closer together, and in a triene, they're closer together as well. They're only one bond apart. Then you get delocalization due to overlap between p orbitals, and this produces some extra stability within the molecule, lowering the enthalpy of hydrogenation. All right, guys, I hope you found that question good or helpful, useful. I'm rushing through these videos now. I'm going to try and bang out as many as I can before the exam. So moving on to the next question. Let's go. Enough waffle.
Keep moving on, keep moving on, keep moving on, keep moving on.
Okay, question 4. The nitration of benzene uses a nitrating mixture of concentrated nitric acid and concentrated sulfuric acid. Which statement is correct? A. The nitric acid acts as a base. B, the nitric acid acts as a catalyst. C, the nitric acid acts as an electrophile. Or D, the nitric acid acts as a reducing agent. So we can go through and basically explain why certain ones are the wrong answer. So if we look here, nitric acid as a catalyst, well, HNO3 it becomes NO2 plus, and therefore that NO2 plus, if you remember in the nitration of benzene, joins the benzene ring, so the catalyst cannot reform. That means that, sorry, HNO3 cannot reform because it's actually used up in the nitration of benzene. So it's not a catalyst because catalysts get reformed. The catalyst in this is the H2SO4 because it forms HSO4 minus, and when the hydrogen is substituted on the benzene ring for the NO2, that joins the SO4 minus to become sulfuric acid again. So that's the catalyst. The next one, it says HNO3 acts as an electrophile. Well, it's not the HNO3 that acts as an electrophile, it's the NO2 plus. It's that nitronium cation that forms the nitrate group on the benzene ring. So that is the electrophile, not the HNO3, although it does come from the HNO3. And then HNO3 acts as a reducing agent. Well, a reducing agent themselves get oxidized. So does it lose electrons or does it gain electrons? Well, let's check the oxidation state. What is the oxidation state of nitrogen in HNO3? It's going to be +5, the hydrogen is going to be +1, and the oxygen -6. And then when it goes to NO2 plus, the nitrogen is also going to be +5, as there's two oxygens, which are going to be -4, and there's an overall +1 charge. So it hasn't actually been reduced or oxidized. So it's not acting as a reducing agent. So that leaves our final answer. It's a base. This question is about nitrobenzene. Nitrobenzene reacts when heated with a mixture of concentrated nitric acid and concentrated sulfuric acid to form a mixture of three isomeric dinitrobenzenes. Write an equation for the reaction of concentrated nitric acid with concentrated sulfuric acid to form the species that reacts with nitrobenzene. So how does the sulfuric acid and the nitric acid come together to make the reactive species that nitrates benzene? So we want to write the formula for nitric acid, HNO3, the formula for sulfuric acid, H2SO4. They're the reactants. Now we want to create this species, which is our important species, the cation, the nitronium ion that is going to nitrate benzene. You can put the plus anywhere above there on the oxygen, the nitrogen, doesn't really matter. And that's NO2 plus. We're going to remove one of the hydrogens from the nitric acid, stick it on a water molecule to make H3O plus, and then we've got a hydrogen sulfide ion, SO4 minus. Super duper duper duper. There we go. We just need to balance it up. So I've got 3 hydrogens on the left. I've got 4 on the right. So I'm going to need to make 5 over here like that. And then I can put a 2 there. And that's going to make 5 in total on the right. So we're now balanced for hydrogens. And we can get on with the next part of the question. Okay, part B, name and outline a mechanism for the reaction of this species with nitrobenzene to form 1,3-dinitrobenzene. So what they're saying is you've got the NO2 plus, the nitronium ion that they talked about in the first part of the question. They're saying name the mechanism and outline how what I've circled there, the NO2 plus, attacks normal nitrobenzene or 1-nitrobenzene to form 1,3-dinitrobenzene. So let's write out the mechanism for that. Once again, pause the video, have a go yourself on some scrap paper, and then unpause and watch the walkthrough. Okay, so here we go. We've got a nitronium ion here, the NO2 plus. Now that's positive. We've got that electron-rich dense area, which is the delocalized ring on the nitrobenzene. That's going to donate a pair of electrons and join it to the nitrogen atom on the nitronium ion. Now, what we need to show here is a broken ring. Nothing dodgy about that. We just need to show a horseshoe with a positive symbol in the middle, and that is our broken ring. So first I'm going to add in our nitro on carbon 1. So we're looking to attack carbon 3, just working out with these horseshoes. One thing, it's a bit hard on the computer, but you've got to be careful that you don't make the horseshoe too big. You must make sure that the ends of the horseshoe do not cross the 2 points around the bond or around the carbon you're adding to. So anyway, there's my horseshoe broken. You're going to get a mark for that. You're also going to get a mark for showing that at the same time the hydrogen atom is joined with the new nitronium ion onto the same carbon. That hydrogen atom is then going to restabilize the ring by donating a pair of electrons to fix the ring. And we show that from a curly arrow. Make sure your arrow has a little curl in it. And now the ring is completely reformed. You don't get any marks for this normally in a mechanism. This is showing the final product. You won't get marks for that, but that's your 1,3-dinitrobenzene. Of course, that hydrogen ion that's been released is going to later on join with the hydrogen sulfite from up above in the first reaction and reform, which proves that sulfuric acid is a catalyst in that first reaction. Awesome. So your marks here were for the curly arrow from the ring to the nitronium ion, and then the arrow returning to refix the broken ring with a positive symbol, and that would get you all those marks. This is electrophilic substitution because a hydrogen atom is being substituted for NO2. All right, let's move on to the next question. The dinitrobenzene shown were investigated by thin layer chromatography known as TLC. We've got 1,2-dinitrobenzene and 1,4-dinitrobenzene shown here in a diagram. In an experiment carried out in a fume cupboard, a concentrated solution of pure 1,4-dinitrobenzene, that's the one on the right, was spotted on a TLC plate, coated with a solid that contains polar bonds. Hexane is used as the solvent, and it's been put in a beaker with a lid. The lid stops evaporation of organic solvents like hexane that have low boiling points. The start line has been drawn, and the final solvent front are shown in the chromatogram in this diagram below. So we've got our start line and we've got our solvent front. Use the chromatogram in the diagram above to deduce the RF value of 1,4-dinitrobenzene in this experiment. So that little circle, okay, is how far the 1,4-dinitrobenzene moved up the TLC plate. You can see how far it's moved up the start line. Bearing in mind that the RF value is the distance the spot has traveled, so how far that spot has traveled compared to the whole distance of the solvent front, we can see that that spot has gone over halfway, right? So if you do distance the spot's traveled divide by the solvent front, you're going to get like 0.6, 0.7. It looks like it's gone over halfway. Okay, if it only went halfway, you get 0.5, less than halfway, you get 0.4, 0.3, etc. So you can see the distance it's traveled is over half. So straight away, when you look at this multiple choice, it's not going to be A or B because they're saying it's traveled less than halfway, and C is about halfway. It's gone more than halfway, so the answer has to be D. We don't even have to get our ruler out and carry out the calculation. Okay, super duper duper. Let's zing to the next question, peeps. Right. State in general terms what determines the distance traveled by a spot in the TLC. So what factors determine how far a spot travels? Remember there was a hexane solvent. Well, it's going to be how well our substance or our spot dissolves in the solvent. Now, another way of saying that is how what's its relative affinity for the mobile phase or the solvent compared to its retention in the solid phase. So what happens when substances move? They spend some time in the mobile phase, which is the solvent, and some time they spend retained on the solid, which is the stationary phase. So it's the relative affinity of each chemical to the solvent or the mobile phase, okay, compared to its retention on the stationary phase. Will tell you how far it moves. So if you have greater affinity for the mobile phase, you're going to move further up the paper, or the TLC plate in this case. To obtain the chromatogram, the TLC plate was held at the edges, placed in the solvent beaker in a fume cupboard. The lid was then replaced. Give something else they need to do. Just make sure when you put the plate in that the solvent is below the start line. If the solvent is above the start line, then the spot's going to dissolve into the solvent and they won't get carried up the plate. So we need to make sure the solvent is always below the start line. Otherwise the spot will run, and what that means is it will just dissolve into the solvent and it won't move up the plate, and we won't basically be able to calculate the RF value, etc. Okay, let's zing now to part F. So a second TLC, thin layer chromatography experiment, was carried out using 1,2-dinitrobenzene and 1,4-dinitrobenzene. So they used both spots and ran them together. An identical plate was used in the exact same conditions with the same solvent. Remember, that solvent was hexane from the first experiment. In this experiment, the RF value of 1,4-dinitrobenzene was found to be greater. That means that 1,4-dinitrobenzene moved further than 1,2-dinitrobenzene. Deduce the relative polarities of 1,2 and 1,4 and explain why 1,4-dinitrobenzene has a greater RF value. Well, let's think about the solvent here. The solvent is hexane. What do you know about hexane? What's its molecular formula? Well, you should know hexane is the molecular formula C6 times by 2, add 2 as it's an alkane, so we've got H14. And you should know the carbon-hydrogen bond is a non-polar bond. There's not a big difference in electronegativity, so this is a non-polar solvent. So the thing that moves further is more of a non-polar molecule. Non-polar substances dissolve really well in non-polar things. Polar substances dissolve well in polar solvents. So the fact that 1,4-dinitrobenzene moved further up the plate, had the greater RF value, means it's less polar, it's non-polar. 1,2-dinitrobenzene, dinitrophenol must be more polar because it's moved further up the plate. So the solvent, why am I putting DNP? It's dinitrobenzene. It's not dinitrophenol. Don't ask me why I put DNP. That's just dumb. Okay, so explanation here. The solvent's non-polar. As 1,2 dinitrobenzene had a lower RF value, it traveled a shorter distance, so showing it had less affinity for the solvent. That means that it doesn't like non-polar things. It prefers polar things, which means that 1,2 DNB is more polar, okay, than 1,4. 1,4 preferred the non-polar solvent, hence why it moved further, had a greater RF value because it had greater affinity for the non-polar solvent than 1,2 did. And that means that 1,4 is more non-polar in its characteristics. Super. Beautiful, beautiful, beautiful. Okay, so that's going to get you both your marks. Let's move on to the next question. And by the way, I shouldn't have put DNP there. That stands for phenol. It should have been DNB, but never mind. A third TLC experiment was carried out using 1,2-dinitrobenzene. An identical plate to that in part C was used under the same conditions, but the solvent used contained a mixture of hexane and ethyl ethanoate. So we now got our non-polar solvent, C6H14, just made of carbon and hydrogen, similar electronegativities, so no polar bonds involved in that molecule. But they've also this time mixed ethyl ethanoate, which is an ester, okay, made from ethanol and ethanoic acid, bonded together in a condensation reaction. And what we know with this molecule is you get the ester link, which has a CO and the carbonyl bond as well, the C-double-O bond. And of course, there's a big difference in the electronegativity of oxygen and carbon. So we're going to have a delta positive carbon and some delta negative oxygens there. I've circled it in green. So this is going to be a polar molecule. So now our overall solvent is got some non-polar characteristics and polar characteristics. The student stated that the RF value of 1,2-dinitrobenzene in this third experiment would be greater. Are they correct? Justify it. Well, of course they're correct. We proved before the 1,2-dinitrobenzene prefers polar. So as this is a more polar solvent, the 1,2-dinitrobenzene is going to have a greater affinity for the polar solvent because it's now got ethyl ethanoate in it, and therefore it's going to move further in the mobile phase. It's going to move further up the TLC plate, so have a greater RF value. And there we go. That's another 2 marks, and that's the end of the question. Don't forget to like, share, subscribe. We're going to move on to the last couple of questions of this pack. It really helps if you hit the like and you leave any comments down below. Once again, I've written DNP here, which is wrong. It should be DNB, but you shouldn't be writing that anyway. I'm just abbreviating it for speed. You should be writing the full name out when you're talking about it, unless they allow you to use an abbreviation. Okay, let's move. Okay, question 6. Use your understanding of the bonding in benzene to identify the compound that has the most exothermic enthalpy of hydration. All you got to do here is check the distance between the double bonds. B, C, and D only have one single bond between the double bonds. So which one of these is going to be more stable? Well, B, C, and D are more stable because there's some overlap between those double bonds. They're close together, they overlap, and this increases delocalization. With A, there's a greater distance between the double bonds. There's 2 single bonds on each side in between the double bonds. So we have less overlap between the orbitals in the double bond, less delocalization, meaning it's not quite as stable a configuration as BCD, which means when you hydrogenate it and add hydrogen and turn it into cyclohexane, it actually does A will release more energy because it's less stable. So it's going from a less stable place to a more stable place. Whereas with B, C, and D, they have a smaller or lower exothermic enthalpy of hydrogenation because they are starting off from a more stable position as they have more delocalization, more overlap between their double bonds. Right, let's look at question 7. 1,4-diaminobenzene is an important intermediate in the production of polymers such as Kevlar and polyurethanes used in making foam seating. A possible synthesis for 1,4-diaminobenzene from phenylamine is shown in the following figure. So we've got phenylamine, and then in step 1, you can see we've had a molecule added to it. In step 2, we've had a nitro group at the bottom. And then in step 3, we have gone back to an amine and a nitro group. And then in step 4, we've turned that bottom nitro group into another amine. A suitable reagent for step 1 is CH3COCl, that is ethanoyl chloride. Name and draw a mechanism for the reaction in step 1. And there we go. Let's get into it. So, for the mechanism in step 1, what's interesting here is this isn't the Friedel Crafts where we're going to add that carbonyl group directly to the outside of the ring. So it's not Friedel Crafts, which is where you get the carbonyl group, use a halogen carrier to make it extra positive, so it's a real strong electrophile and it attacks the delocalized ring and temporarily breaks it. No. This is added on to where the NH2 is, and it's substituted for one of the hydrogens on the NH2. This means it's actually a reaction of the side chain, and here you need your knowledge of amines reactions rather than your knowledge of directly of aromatic reactions. So with aromatic mechanisms, you've also got to know your other organic groups mechanisms because they can be side chains coming off of the benzene ring, and it could be them that's getting attacked. See, I've circled here, it's the amine that's being attacked, not the delocalized ring. So what's going on here, we're going to draw our benzene out and we're going to put our amine with its little lone pair there. Okay, what's the lone pair going to be attracted to? Remember, positive can't move, only pairs of electrons can move. We've kind of got a delta positive carbon here on the ethanoyl chloride, so we're going to have our lone pair of electrons moving to form a bond here. So now what we need to do is we need to redraw the intermediate. Now what's going to happen after? Well, also that double bond is going to need to break. Why? Because carbon's in group 4, it can't have 5 bonds, and if it maintained the double bond to the oxygen and the new bond to the nitrogen, it would have 5 bonds. That's impossible. So it has to sacrifice a bond. So it temporarily breaks that oxygen bond on the carbonyl group. We know that's going to reform. You've got to know how to draw it in its new form. So we've got this new bond to the carbon, and then we've got that single bond to the O where it was a double bond, and we show the lone pair. I need to put a negative symbol there as well. We've got the methyl group coming off from the chlorine atom. So now we've only got 4 bonds around the carbon. That sounds great, but we've got this unstable oxygen, which is a lone pair and a negative charge. So what it does is it donates the lone pair back to the single bond to reform the carbonyl bond. So it's going to reform the COO, and the chlorine is going to break off. Now we look at our nitrogen, which is a nitronium or whatever cation. It's got a positive charge on it. Look, it's got 4 bonds. Nitrogen likes to have 3. You need to bear that in mind. So one of these bonds has got to go. And one of the hydrogens, any of these 2 hydrogens, is going to snap and donate its pair of electrons to that positive charge on the nitrogen atom. And that's going to stabilize everything there and mean it only has 3 bonds around it. So this is where the rest of the marks are. And you need all of these different bits, curly arrows and lone pairs to get the marks here. You do not need to, as normal with mechanisms, draw the final product unless explicitly or specifically stated in the question. You don't, but I always like to show you the final product. So here we go. And of course, what do you think the side group's going to be? We're going to have a hydrogen ion coming off, and you're going to have a chloride ion coming off, aren't you? So there we go. Wunderbar. Right, moving on. Part B, the product of step 1 was purified by recrystallization as follows. The crude product was dissolved in the minimum quantity of hot water. They put that in dark black. That means it's really important and part of the answer to the question. The flask was left to cool to room temperature, again in bold or dark black. And then it says the crystals formed were filtered with a Buchner funnel and a clean cork was used to compress the crystals in a funnel. So again, and a little cold water was poured. Those bits in the bold black are really important and are keys to answering this type of question. So it says, give a reason why the minimum quantity of hot water was used. So you can tell what these questions are all going to be about, the things in bold. So why do we use only a little bit of hot water? Well, it's to ensure that the water is fully saturated with crystals. So we want to ensure full saturation of the solution with crystals. If you use lots of water, um, it would dissolve all the crystals and it wouldn't be a saturated solution. Now, for the second part of the question, it says the flask was cooled to room temperature before the crystals were filtered off. Why did they cool the flask to room temperature before the crystals were filtered? Well, as we decrease the temperature of the solution, the solubility of the liquid decreases. So its ability to hold on to crystals decreases and we'll get crystals crystallizing. So what we're doing here is we're lowering the temperature, and as the temperature is lowered and cooled, the solubility of the solvent, the liquid, decreases. Its ability to dissolve the crystals decreases as its temperature decreases. And that means we'll get crystallization and we'll make sure we get the maximum yield possible. Cool. So for the last part of this question, it says this slide that we're on at the moment, it says the crystals were compressed into a funnel. Why did they squish them up? This is to force the air to pass through the crystals. It removes all the air gaps between the crystals, and therefore the air is forced to go through the crystals instead of through the gaps in between. Right, a little cold water was poured through the crystals. So why did we pour some cold water on the crystals? Well, that is to dissolve soluble impurities. So any impurities that are soluble, they'll be dissolved in that little cold water and can be removed. Okay, part C. The melting point of the sample in part B was found to be slightly lower than the data book value. So the melting point, we're not quite fully accurate on that, suggests the most likely impurity to have caused this low value and an improvement to the method so that a more accurate value for the melting point could be obtained or would be obtained. Well, it's likely when we added that cold water to remove the soluble impurities in that last step, that water, which has obviously a melting point of 0 degrees, which is going to be less than our other substances, that's likely to have lowered the overall melting point slightly. That little bit of water and the removal of that water will ensure a more accurate result closer to the data book value. And we can do that by air drying it or pressing it between some filter paper using our fingers. Okay, the figure here is repeated. We've got the same reaction mechanism we looked at before, the exact same reaction mechanism from the start of the question. In an experiment starting with 5.05 grams of phenylamine and 4.82 grams of purified product were obtained in step 1. Calculate the percentage yield in this reaction. Give your answer to the appropriate number of significant figures. So we have to remember the equation for percentage yield. This is a 3-marker. So percentage yield is equal to the actual mass divided by the maximum theoretical mass that we can achieve. Okay, times it by 100 and you'll get it as a percentage. Now, they told us in the question that we actually achieved 4.82 grams of purified product were obtained or achieved in step 1. So we know the actual mass is 4.82. We need to find out the maximum mass of purified product we can get. So we're going to need to use mass over mR times moles. We started with 5.05 grams of phenylamine. So we can find the moles of phenylamine by doing 5.05 grams divided by the MR. Now, what's the MR of phenylamine? Well, it has the formula C6H5NH2. So add that all together and you'll get 93. So we want to do 5.05 divided by 93, and that's going to give us 0.0543 moles. And that's going to get you your first mark. Now, if we look at the reaction mechanism, you can see from that reaction mechanism above, it's a 1-to-1 reaction. So we get, for every mole of reactant, phenylamine, we get 1 mole of product. So we're going to get 0.0543 moles of the product created. Ta-da! Now all we need to do is turn that 0.0543 moles of product into grams of product. We've got moles of product, we need to times it into grams. Now, how do you do that? Go back to your triangle, and we're going to need to do the MR of the product times the moles of the product. Now, what was our product? Well, in step 1, it was going from phenylamine to C6H5NHCO CH3. And if you add all of that up, you get an MR of 133. So we want to do 133 times the moles of 0.0543, and that will give us a maximum mass that we should have got of this product of 7.33 grams. So we should have achieved 7.33 grams if we started with 5.05 of phenylamine. Instead, we got 4.82. So we do 4.82 actual mass over maximum mass, which was 7.33 times 100, and you get something like 65.76. And then you can round to the appropriate number of significant figures. A level, we tend to go to 3 significant figures, so like 65.7 or 65.8, 65.80, whatever. We ignore the 0, but there we go. Right, that'll get you 3 marks. Let's move on. We're on E. A reagent for step 2 is a mixture of concentrated nitric and sulfuric acid, which react together to form a reactive intermediate. Write an equation for the reaction of this intermediate in step 2. Oh my days. They are asking us to rewrite the old nitric acid and sulfuric acid equation. Dead easy. That forms a reactive intermediate. Well, it's just sulfuric acid plus nitric acid makes the NO2 plus H3O plus. We did this earlier in this pack, plus HSO4 minus. Balance it up. 2 in front of the HSO4 minus, 2 in front of the sulfuric acid. Bob's your uncle, Fanny's your aunt. Boom, equation done. Now, where are we? Yeah, so we are looking here. Next part to the question, name a mechanism for the reaction in step 2. This is going to be electrophilic substitution. And that's because you're swapping a hydrogen atom for the NO2 around the outside of the benzene ring. Right, suggest the type of reaction occurring in step 3. So we now got a zing to step 3, and identify the reagents in step 4. Let's zing to step 3, zing in. We're going from there, and we are getting rid of the, we're going from the NH2 to NHC, we're going from NHCO CH3 to NH2. So what you've got to look here is we're hydrolyzing this bond. We're breaking this bond by adding water. And what in fact you're going to get, we're going to add a hydrogen to make NH2, and the OH from the rest of the water molecule will be smashed onto the side to make ethanoic acid with the CO CH3. So you should be able to see that. If you add water to here, you add a bit of H2O, one of the H's goes on to the NH2, which is attached to the benzene ring, and then the C carbonyl CH3 gains the OH from the water molecule and becomes ethanoic acid. Lovely jubbly. Let's go to the last part. And the last part of the question, and the last part of this pack, is identify the reagents used in step 4. So let's smash up to step 4 and look at what reagents. Well, step 4 is where we're turning the NO2 group, which you will see at the bottom here. We're turning that NO2 into NH2, into an amine group. And how do you do that? You do reduction. So we're going to reduce it and hydrogenate it. Now, you could use hydrogen with a platinum, palladium, or nickel catalyst, but in AQA, they tend to like you to say hydrochloric acid with a tin catalyst, and that is used to reduce or you do hydrogenation. And there you go. That's the end of the pack, guys. So hit the like, share, subscribe. Let's get to the marks. I'll see you in the next video.
You're still here? It's over.